In this video, we will be elucidating on the relationship that there is between normal vectors and planes. We will essentially see that these types of vectors can help us to represent a plane mathematically through an equation. First of all, we need to specify what we mean by a normal vector. When we talk about normal vectors, in this case, in this video, we'll be talking about normal vectors to a plane. Let's draw out a line that is perpendicular to that plane. And so, first of all, you have to visualize it in 3D. Essentially, we have a plane, and we have a line that is cutting through that plane in a perpendicular manner. And so, formally speaking, a normal vector to that plane is essentially a direction vector to that perpendicular line. And loosely speaking, a normal vector is a vector that is perpendicular to that plane. And so I've drawn out my normal vector here. And what we note is that the normal vector gives the direction of that red line. But that red line is perpendicular to that plane. And therefore the normal vector is the direction vector of the line that is perpendicular to the plane. But I want to touch on the fact that there isn't a single normal vector for a plane. There's actually an infinite number of normal vectors. For example, n might be a normal vector, but 2 times n is also a normal vector. In addition, a normal vector cannot be equal to the zero vector. And this might seem obvious, but you will see it's important in order to understand the link between normal vectors and planes. For the remainder of this video, I'll be using the elementary technique that consists of using points rather than position vectors. And this is just to make my explanations more clear. First, I'm going to state that if we have a normal vector to a plane, as well as a specific point, for example, let's call it A, then we have enough information, mathematically speaking, about this plane. In other words, any point on the plane can be described by the normal vector and that point. To prove this, let's consider any point in 3D space, which we will call B. So this point can be anywhere in space. It can either be on the plane or outside of the plane. But what are the conditions for a point B to lie on our plane? Well, we can clearly understand that if we have a vector joining point A and B, well, if B lies on our plane, then the vector AB has to be perpendicular to our normal vector n. Well, that is loosely speaking, but in mathematical terms, vector AB has to be orthogonal to n. So orthogonal is the equivalent of perpendicular but for vectors. Mathematically speaking, this means that our vector AB dotted with our normal vector to that plane n has to be 0, because this statement means that the two vectors are orthogonal. But why is that actually the case? Why do the vectors have to be orthogonal? To prove why this is the case, let's consider what we call the orthographic projection of point B onto our plane. The orthographic projection of point B onto the plane is the projection of B, which is therefore a point, because B is a point and therefore its projection will also be a point. And so it's a projection on the plane, and we will call that projection C. But C has a specific characteristic. It has to be on the line that is perpendicular to the plane passing through point B. In other words, point C has to be placed in such a way that the line joining point B and point C is perpendicular to our plane. And we call C the orthographic projection. Ortho comes from the Greek straight or placed upright. And this makes sense in this case because the orthographic projection basically gives us a line that is at right angles with our plane. Hence, the prefix ortho is used to describe anything that's at right angles with something else. In other words, perpendicular. Now, going back to our original question, which was trying to figure out why this equation over here essentially dictates whether our point B lies on the plane or not. Well, we can see that we can write our vector AB in a different form. Indeed, our vector AB can be rewritten as the vector AC added with our vector CB, which means that we can rewrite this equation as AC plus CB dotted with our normal vector N. So now if we distribute, we get that AC dotted with N plus CB dotted with N is equal to 0. Now we know that vector C lies on the plane because it's the orthographic projection of point B onto our plane. Therefore, the dot product of AC with N is 0. This implies that this dot product over here is equal to 0. But we know that our normal vector cannot be equal to the 0 vector. And therefore, there are two cases. Either CB and N are orthogonal, or CB is the 0 vector. But clearly, CB and N are not orthogonal, because remember, C is the orthogonal projection of point B onto the plane, and therefore the line CB is perpendicular to the plane. And if it is perpendicular, our vector CB has to be parallel to our normal vector N, because our normal vector is also perpendicular to that plane. Since CB and N are not orthogonal and N is not the 0 vector, this means that CB has to be the 0 vector. So let me reiterate this because this is important. There are only three ways for a dot product to be equal to 0. Firstly, the first vector is the 0 vector. The second way is that our second vector is the 0 vector. And finally, the third way for the dot product to be equal to 0 is that these two vectors are orthogonal. But we know that by definition the normal vector is not the 0 vector. So that leaves one out of the way. Moreover, we know that the vectors CB and N are parallel, so by definition they can't be orthogonal. And therefore this means that our vector CB is actually the 0 vector. Note that the fact that I have underlined the 0 over here means that it's a vector. Since our vector CB is actually the 0 vector, this means that our point C is actually equal to the point B. They are placed in the same location. But we know that by definition our point C lies on the plane because it's the orthographic projection of point B onto the plane. Therefore, since C is equal to B, B also lies on the plane. And note the equivalence relationship that we have over here. If the vector AB is perpendicular or orthogonal to our vector N, then this implies that B will lie on the plane. But it not only implies, it's an equivalence condition, which means that if B lies on the plane, then our vector AB dotted with N will be equal to 0. In other words, they're orthogonal. In conclusion, we can see the importance of normal vectors when we consider planes, because essentially, if we have a normal vector and a point A on the plane, then we can know whether any point, any arbitrary point B lies on the plane or not. And it lies on the plane if and only if the vector AB is orthogonal to our normal vector N. Thank you for watching this video. If you have any questions, leave a comment down below, and if you enjoyed it, don't hesitate to drop the like button.